Okay, hello everybody, and welcome to today's Turing lecture. My name is Chris Williams. I'm the University Liaison Director from the University of Edinburgh. So just to remind you a bit about the Alan Turing Institute, it's a joint venture between 5 universities and EPSRC. And although, of course, from hearing about those universities, you might think that this is a very academic kind of thing. Of course, we're very interested in the real world of data science, and therefore it's very appropriate today that in our lecture series, this fourth lecture in our lecture series is about industrial and commercial work, and we actually are very fortunate to have 2 speakers today from those different areas to tell us about their work. So the first one of these is Tim Harris from Oracle Labs in Cambridge. Tim did his BA and his PhD in Cambridge. From 2000 to 2004, he was a faculty at the Computer Lab in Cambridge. Then, I believe, from 2004 to 2012, you were at Microsoft Research in Cambridge. And then in 2012, he left to found the Oracle Labs in Cambridge. Okay. And Tim's research interests span, it says here, multiple layers of the stack, including parallel programming and, for example, specialized architectures for particular workloads. And today he's going to tell us about system challenges in graph analytics. So without further ado, Tim, thank you.
Thank you. So we needed to commit to titles for the talk some months ago. And so I chose a fairly general title, Systems Challenges in Graph Analytics, which would span much of the different topics that we've worked on in Oracle Labs. And then I came to be thinking about, well, what exactly would I cover today? I thought that a nice point to emphasize would be what the role of the operating system is in these kind of workloads and the ways in which it presents different challenges to previous workloads that we've designed and optimized operating systems for. So I'm going to talk about a few of the difficulties that we see in running graph analytics workloads efficiently at the moment, and then a little bit about some possible future directions that I think would be interesting for research. I should maybe say a little bit about Oracle Labs. Our Cambridge office at the moment is 6 people, and we're part of the larger organization of around 200 people split across a range of sites, Redwood Shores in the US, Zurich, Brisbane, Australia, plus other researchers from multiple countries. The kind of work that we do has to be rooted in problems that we see having significant impact in the company. So before starting work, we need to identify what would be the potential transfer targets for that work. But also we're doing research. We need to identify why this is not just an engineering effort that other groups within the company would be handling, and we're generally doing work with a view to academic publication. And some of the work I'm talking about today is coming from recent publications. Some of it is work we'll be hopefully getting accepted and presenting at conferences in the near future. I'm not going to read out all the small print, but because of the recording, I should just emphasize this is me talking about some research projects. It's not me talking about our own products. And when I'm talking about benchmark results, these are our own implementations of these algorithms. It's not presenting official recognized benchmarks. So the area that runs through this talk is in-memory graph analytics. And this is an area that we've been working on in Oracle Labs for many years now, motivated by the fact that there are many data sets that have a natural representation as a graph that's maybe better suited to the data than a representation in traditional database tables. So representing entities and the relationships more explicitly, and using this to solve queries such as identifying important users in a social network system, identifying the impact of some advertising on the results that are seen as a consequence, searching through data sets describing people and the interactions between them for examples that match particular patterns. So there's a lot of different problems like this, often tackled with large data sets, tens of gigabytes, potentially multiple terabytes of data or larger. and which do not have as natural a fit or as natural an implementation with traditional database tables and join operators are expressed over them. Now, the approach that we're taking in our current work is to split the solutions across multiple levels. At the highest level, we're looking at domain-specific languages for expressing queries over graphs, and we've got a variety of different languages suited to different kinds of queries. So one example would be a specialized language for subgraph isomorphism problems, where we're taking a little pattern of a graph and saying we want to find all of the instances of that pattern within some much larger multi-gigabyte, multi-terabyte data set. We've got other algorithms, other languages for algorithms which are closer to the ones I'm talking about today, where we're looking at more at traditional graph analytic workloads, say iterating over all of the vertices in a graph and all of the edges in the graph and deriving properties based on those. So as a running example, I'll be using PageRank, which I'll go into a little bit more detail in a few slides. But other examples here would be classical graph problems of identifying strongly connected components, identifying centrality metrics for different vertices in the graph, these kind of issues. So we start out with nice code at the top expressed in terms of graph concepts written by someone who understands the problem that they're trying to solve. And then my parts of the stack are lower down, where we map these algorithms into C and Java code and use a parallel runtime system that expresses the ability to iterate over the graph vertices and to perform the kinds of computation that we want to do on each of these. So the example here, we've got a little fragment of code in a C++-like language, and we have a library and runtime system built entirely in standard C++ that lets us write this kind of parallel iteration over the graph vertices. And then the implementation maps this parallel code onto the physical structure of the machine, the multiple sockets with the processors in, the memory connected to those sockets, and the other resources, the network interfaces and so on, if we're looking at a distributed implementation on a cluster. And what you might see here is that a lot of the work that we're doing here within our own system built in user mode is really replicating the kind of traditional activities that you might expect that the operating system would be doing, the kind of activities that Unix, Linux, Microsoft Windows, other systems would be doing. And we're not really getting as much support from the underlying operating system as we might expect. We're having to repeat a lot of the OS functionality here within our workload. And maybe that's reasonable if we just have one of these workloads running on a machine and are happy dedicating a lot of expertise to optimizing it. But this is not a good general place to be. If we want to run a mix of workloads sharing the resources of a machine, and we want all of them to get good performance without needing to go through the kind of optimizations we're doing in research projects within the runtime system here. So we end up having this state of affairs where the query engine and the runtime system are repeating a lot of the OS work, trying to isolate concurrent queries from one another in terms of the performance they receive, abstracting the hardware, mapping the parallelism in the workload efficiently down onto the features that the hardware has. And we'd like to get more support from the OS or from common system software for these kind of functions rather than repeating them in each workload we study. Now, a common theme in the examples I'll talk about is that the difficulty in part is coming from the complexity of modern hardware and the fact that the hardware really needs to embody that complexity in order to deliver good performance. And here's one example just to illustrate what I mean by complexity in this setting. And this is the structure of the SPARC M7 processor, a fairly recent processor built by Oracle. And this is just one socket of this processor, which itself may be formed into a larger multi-socket system. Within the processor, we've got an on-chip network used for communication between the different elements here. We've got 8 of these units called a core cluster, which internally has 4 processor cores, and each of those cores can run in hardware 8 different hardware threads with sharing of the resources between the threads as they have execution to run and not. And then we have multiple levels of caching. So we have caches private to the core. We have caches that are shared between pairs of cores that are nearby, shared between the entire core cluster and within the complete socket by communication across the network. And then we have these off-chip links which connect the socket to the memory. And consequences of this are that the performance of software can depend a great deal on exactly how its execution is allocated to these different resources in the hardware. Because if we have two threads running in the same core that want to communicate with each other, then that's very efficient because they share this fast cache memory that's directly accessible to them. If they're running on different sockets, then they've got to go over much slower links between the sockets to communicate. And if threads are accessing different locations in the computer's memory, then the time it takes to do that will depend on whether they're making access to this memory here directly connected to the socket they're running on, or whether they have to go across the links that connect the machine together. And getting all of these decisions tuned for a particular workload is complicated because it's going to depend on the actual structure of the computation, the generated code that comes through multiple levels of compilation from the original graph analytics DSL code. It's also going to depend on the dynamic state of the machine, what other workloads are running, where memory is allocated, where memory is available for allocation, and so on. It's also going to depend on the input structure of the graph. And so if a graph has vertices that can be partitioned well between the sockets, then maybe it's possible to allocate resources in one way. If the graph has lots of edges that cross almost randomly between the vertices, then we've maybe got more traversal needed while exploring the graph. So all of these factors go into making a good mapping from the software down to the hardware and need to be handled well in order to get a good performance. So I'm going to go through 3 case studies now of areas that we've been working in and illustrate the kind of techniques that we apply in order to benefit from the good performance in modern hardware and to relate that to the kinds of analysis that we're wanting to do. And as you see, these are functions which you would expect would be traditionally the role of the operating system. Deciding how to distribute work within the machine, deciding how to allocate memory, and deciding where to place the threads that are forming part of the computation. So just to go back to the example here of the PageRank algorithm, what we're doing here is iterating over the vertices in the graph. We've got a value that we're trying to derive for each vertex, indicating a kind of metric of the importance of that vertex. And we're going to iterate over all of the vertices multiple times and converge on final values for these per node values. So if we look at what's happening when we're processing node 10, the node with value 10 in the middle here, we iterate over all of the neighbors of that with incoming edges to the node we're interested in. We sum the current values of those neighbors, weighting them according to the number of outgoing edges that vertex has. So these contribute all of their weight, and this one over here on the right contributes half because it has 2 outgoing edges. We sum these together, and then there's an additional scaling step, but we get a final value for this vertex as a result. And you can see that this is an algorithm that has abundant parallelism and would be a good fit to a system like that M7 system where a single processor socket has 256 hardware threads, because we can process each of these vertices independently and manage these intermediate values by effectively double buffering, having one block of memory for the current value and another block for the next value. But the challenge in getting efficient parallelism here is that there's a trade-off between the granularity at which we distribute batches of iterations, batches of graph vertices between the threads, and the overheads that we incur from doing that distribution. Now, if we think about a couple of extreme cases, if we started out by distributing just one vertex at a time to each of the threads that's working on this problem, then we're going to get good load balancing. We'll find that we keep all of the threads busy throughout the computation, and they'll all finish at roughly the same time at the end. But we're going to have a lot of costs involved with actually doing this work distribution, because each time a thread becomes idle, it needs to fetch a new piece of work, and that communication is going to compete for resources with other work distribution and with the actual useful memory accesses that the computation is doing. And at the other extreme, we could just divide the vertices into large batches and say give a thread a block of 1,000 vertices to process each time it needs extra work to do. And that's going to reduce the overheads that we incur in distributing the work, but it's also going to have the risk of load imbalance if some of the threads finish their work early while other threads are still sitting on blocks of vertices that they're in the middle of processing. And this is actually a significant problem with a lot of social network graphs, where there's a high degree of load imbalance between the number of edges on each of the different vertices. We've got some actual numbers here, just plotted on a normalized scale taken from one of the data sets we use. And there's differences of thousands or millions to one, depending on the data set, between the most highly connected vertex and the least connected. So celebrities have lots of links. I don't have many followers on Twitter. So that pushes us towards trying to distribute the work in a fine granularity so that we don't find that one of the threads has been left with a large block of work at the end of the computation while other threads are idle. Now, we have some examples here from an earlier version of our system before we tackled this problem of efficient work distribution. And what we're showing is the number of threads that we're using for the computation. And this is on a machine with just over 1,000 hardware threads available. And we're showing the batch size that we distribute the vertices in. And so what we can see is that if we use about half of the hardware threads and a batch of about 1,000 vertices, then we get the best performance indicated by the lightest squares. And if we step outside this and make the batch a bit smaller, or we use fewer threads, then the performance drops off rapidly. So we can tune the workload if we're happy to do so and get to this square and get good performance. But the performance is very sensitive, and if we're not making the optimal tuning choice, it's not just a few tens of % that we're losing. This is going down to a factor of 4 worse than the optimal. So the techniques that we've been developing here are to make it possible to distribute work on a fine-grained basis while retaining efficiency. And the key to doing this is to make sure that the runtime system that's distributing the work is aware of the structure of the machine, and that the way it distributes work maps naturally to the hardware in the machine and the places at which the hardware can communicate efficiently. So let's see what happens in an example if we pick a tiny graph with 16,000 vertices, and we try to distribute them in batches of 10. Then what we're going to do first of all is to split the work initially between each of the different cores in the machine. So in this system, a core has a substantial private cache, and it's got multiple hardware threads. So the idea is we will distribute work coarsely between these cores, and then we'll have efficient synchronization within the core for distributing work between the individual threads. And we'll then have a mechanism to rebalance the work if it happens that one core runs out of work before the others. But that's going to happen relatively rarely, and so the cost of that complexity is less significant. So in the common case, what we do, we distribute the work between the sockets and then between the cores within the socket. So in this case, the 16,000 vertices shared evenly between 128 cores gives us 125 vertices on each of the cores. So this is meaning that when a thread wants work, it's able to fetch it from its local core, hopefully still in the local data cache for that core, without having to communicate across the slower links to a remote core or to a remote socket in the machine. And the second piece of the technique is to aggregate requests for work between the multiple hardware threads that share a core, and to exploit as much as possible the fine-grained synchronization available within the shared cache that the hardware threads have. And the technique we're using for this is to have flags that a thread can set when it's about to run out of work. So what we're doing is, instead of having a thread process a batch of graph vertices and then go and fetch more work, it's going to put up a flag when it's getting towards the end of its current batch of work. And that flag is going to be monitored by other threads, and they're going to respond to the request and ideally distribute the work out to the worker thread before it actually runs dry and needs to stall waiting for new work. So what should happen is that as threads get towards the end of their current batch of work, they start setting the flags indicating that they're getting towards the end. Whichever thread actually finishes first will then look at all of the threads in its own core. It will then make an aggregate request for work from the per core allocation of work and distribute that back out again to the individual threads. So what's happening is that when we need work, we're hopefully finding it's been distributed out to us already. And when we need to synchronize in requests, we're doing so within the efficient cache that's shared between the threads in the same core. And we're hopefully avoiding all but infrequent communication across the other links in the machine. Now, the result of this is that we get an improvement in the actual peak performance for the algorithm. But perhaps more significantly, we get an algorithm that is much less sensitive to the exact choices of how it's configured and to the machine and the graph that it's running on. So with the same example as before, we've got the example that we had with the baseline system here, and with the new work distribution technique, instead of having this sensitivity, we've got good performance across a wide range of batch sizes and a wide range of thread allocations to the job. So we're removing the need for that per workload, per input graph tuning step, and we're able to push down to smaller batch sizes and be able to benefit from more fine-grained work distribution for very imbalanced workloads that would benefit from this. So the next resource I'll talk about is allocating memory for running the PageRank algorithm. And the challenge here is deciding exactly where in the machine to allocate that memory in relation to the threads that are running. So which sockets it should be attached to and how to spread the work around the different sockets. And making good decisions here depends a great deal on the access patterns of the workload and also on the assumptions that hardware designers have traditionally made about how memory is going to be accessed and what they're going to optimize for. And the point to keep in mind here is that hardware is traditionally designed with sequential access patterns as the fast path that's going to be handled as efficiently as possible. So if we have a large block of memory and we're iterating it through sequentially, then there'll be techniques in the hardware and in the compiled code and in the microprocessor that will handle prefetching data into the local caches and will make sure the data is ready when it's needed. If we're making random accesses, then that tends to be handled less efficiently if we're dotting around from one piece of memory to the next. So if we look at what the PageRank algorithm in this implementation is doing, we represent it using a compressed sparse row format, which is an efficient binary format to represent this in memory. We've got one array with an entry for each of the graph vertices, and that entry is identifying the start of a run in a second array holding entries for each of the edges. So these two arrays describe the structure of the graph. And if we think about this vertex here, then these entries in the edges array are giving the vertex numbers for the adjacent vertices for that one that we're processing. So what we do for the PageRank computation then is we start from a vertex, we go along this run of vertices within the edges array, we load in the previous PageRank values out of the current values array, and we sum these and upscale them, and we get a new value to put in the output array. So the access patterns here are a mix, with some of the arrays being accessed sequentially, and then some of them being accessed at random. Now, the vertices array and the next array, we're accessing once for each vertex we process. But then if we've got a batch of vertices, even if it's only a small batch, then we're going to be stepping through them sequentially. And typically, the graphs we're processing have many more edges than vertices. So the traversal of these two arrays is handled relatively well by hardware. The edges array is also handled well because we're iterating sequentially through a batch of edges in this array. And if we go on to the next vertex, then we're just continuing where we left off with the edges for that next vertex. So we've got long sequential access patterns which are also going to be handled well. And the challenge is this current values array, where we're making these accesses dependent on the edges that we find. And if we've got a large number of nodes in the graph, we're accessing all over the point here, and this array might be many gigabytes in size, and depending on the structure, we might find that this is about the worst possible case in terms of access patterns. So let's see what the impact is of some of the different choices we can make about placing memory within the machine. And what I mean by placement here is choosing where the actual physical memory locations that we access are located on the system. So the process that's doing the computation, as far as it's concerned, is going to see a nice contiguous block of memory for each array. But either the runtime system code we're developing or the operating system is responsible for mapping that onto the physical memory modules in the machine and controlling the translations, controlling if it's a machine with multiple sockets, then which pieces of which of these arrays go on different sockets from one another or on the same socket. And the difficulty of doing a good job here is made all the more important by the physical structure of the largest machines that we're working on. The example here is a 16-socket machine, which is a full rack in size. And in addition to the structure within each of the processors, we have groupings of 4 processors with fully connected links between them, and then a switch in the middle of the machine that is used for communication between pairs of processors that do not have the fully connected links. So we end up with very different access patterns, characteristics, depending on where the memory we access is located. If it's on our own socket, then the processor accesses it directly. If it's on the same of these clusters of 4 sockets, then it's one hop away on the network. And if we need to go through the switch, then that adds an extra hop to the access. So we get different timing characteristics here and potentially different bandwidth capacity constraints. We can see that in a simple example where here we're just running a single thread at a time, and we're choosing between whether the memory is placed on the same socket as the accessing thread, the lower red bars here, or whether the memory is distributed across all of the sockets. We're plotting the execution time on different machines on different data sets, and you can see that we're getting 30–40% improvement if we have the memory accessible on the local socket at all of these accesses. Now, if we go on to a more complicated parallel workload, then the initial version I'll show is using the operating system to distribute the memory roughly evenly across the sockets. So it's not going to be exactly even because this might depend on the state of the system and where there's more or less free memory, but it's going to do a good job of making this roughly balanced. In this case, if we look at the performance of PageRank on a graph of about 16 gigabytes in size, then we're showing on the y-axis the speed up that we achieve over that single-threaded optimized implementation. And on the x-axis, the number of threads we use, from 8 going up to 512, which is using 1 thread per core, on this 16-socket machine. And if we look first of all at the 1 to 512 case, then we're getting pretty good scalability. We're getting a speed up of just under 200-fold from 1 thread to 512. And part of that is that sequential overhead that we saw based on the same socket versus different socket placements. So we're getting reasonable performance in terms of scaling, but we're not necessarily getting the peak performance that we could get if we control the memory placement explicitly. So the next version is, rather than relying on the operating system to distribute the memory, doing that explicitly within the PageRank implementation, and making sure all of the memory is split evenly between the different sockets, and controlling the translation sizes that we use for these allocations. In particular, making sure that the array of intermediate values is controlled by fine-grained small allocations that let us distribute that load very evenly across the different sockets, because the access patterns to that array are so critical to performance. And if we do this, then we get a slight improvement at the peak performance. And if we were to zoom in at the smaller sizes, we get a more significant improvement there, where we're mapping the memory over the subset of the machine that's actually active with this workload. And so we're avoiding the number of remote memory accesses that need to cross the switch in the middle of the machine. The next step we might try is to trade off some of the extra capacity we have in memory for better performance. And what we're doing here is replicating the graph on all of the sockets. So instead of having to access the graph remotely when it's not a portion that's local to us, we've always got our own local copy available. And so this is making it look a bit more like a distributed system, even though this is a single machine, because we're replicating this graph and using that to avoid some of the remote communication we'd otherwise need to use. And this gets us some more significant benefits in the peak performance, and we're now up to somewhere around 240-fold increase over the baseline. But the difficult factor is still these accesses to the current page rank values, where that array is being updated each iteration of our algorithm. And so we can't just simply replicate it once at the beginning and then access a local copy, because we need to have the up-to-date values from the previous iteration. So what we can do there is, again, make this a bit more like a distributed algorithm, and in between each iteration, re-replicate the set of PageRank values to each of the sockets. And this is a technique that comes up in a couple of the other examples. We're adding extra work to the algorithm, adding this replication step where it's not otherwise needed. But an effect of that is to speed up another part of the algorithm, and the speed up we get is more significant than the replication costs that we're incurring. So what happens here? We've now got above the 250-fold speed up against the best single-threaded performance we could achieve. And compared with the version with one thread and all the memory distributed across the machine, we're around 440-fold speed up. So this looks reasonably good if we're just considering the part from 8 up to 512 threads. But you can see here that we're not getting any extra benefit when we go beyond that point where we have one thread per core active. And the cores in this machine have 8 hardware threads, and so we'd like ideally to be able to benefit from that extra processing resource. Now, the difficulty for why we're not getting any benefit from those hardware threads comes down to the way in which the memory accesses are being fetched into the processor, and the fact that each time we're making those random accesses when accessing the current values array, even though it's efficient in the sense it's going to our local socket, we're not getting any benefit from all the levels of caching that exist between the thread and the memory. Because on these large graphs, the current values array might be 0.5 gigabyte or 1 gigabyte in size, and the caches here are 8 megabytes, so pretty large per core cluster, or 64 megabytes for the complete chip, but nothing like the complete size of that array that we're making repeated accesses to. So the way that we need to approach this to get better performance from a single socket is to try and make better use of the caches and turn some of these cache misses where we go directly to memory into accesses that are going to be held already in the local cache within the socket we're running on. And a technique we can use for that is cache tiling, where we distribute the graph into sections, and we arrange that we process an individual section at a time and hope that the part of the randomly accessed array is going to stay in the local cache of the processor as it's running. So what we'll do here is we'll take the current array, we'll split that apart into multiple pieces, roughly sized according to the last level cache of the socket we're running on. And then we will create a separate copy of the piece of the graph that has any of these edges going through the part of the array that we're accessing. So again, we're adding extra work, but the hope is that we'll not suffer much because the accesses to these other arrays are very efficient, because they're all sequential accesses. And the random accesses here are going to become efficient because we won't be needing to go to the main memory quite so often. We'll be getting more cache hits. And also we add a final step because we might have results that have to be aggregated from between multiple tiles of the work into a single final result for that vertex. So we might have some edges, as in this example, going through different tiles. And the result here is that we can push the scalability beyond one thread per core, and indeed even at one thread, get an improved performance at that level. So we're over 600 times faster at the peak performance. I'm just looking at some examples now on a larger graph. This is the scale 30 input graph. We're now able to get scalability up to the complete size of the machine. So going from 512 threads up to having, in this case, all 7 threads active, and there's a slight extra benefit from adding an 8th one as well. So the result is that by controlling the memory placement explicitly, we're able to change a workload where we got around 500-fold speed up in this case, just using the default operating system policies, into a workload where we're getting over 2,000-fold speed up. And that translates into a result at the right-hand side of this graph taking around 12 seconds to compute, and the corresponding single-thread version that we're normalizing against taking around 10 hours to compute. So we end up with significant improvements in this case. So just for the last of these examples, I'll talk about the choice of exactly where threads are placed within the core and the sharing between threads running on the same core and the impact of the different work that they're doing. And the challenge here is not so much in this PageRank example, but in cases where we have a mix of workloads that we want to run together. So perhaps different analytics jobs processing the same graph at the same time, but doing different kinds of computation and a different mix, say, of integer and floating point computation, or memory-intensive and CPU-intensive computation. And the difficulty we're faced with is that the actual performance we get depends a great deal on the workloads and how they interact within the structures within the core. And what we've got here is looking just on an Intel 2 threads per core system. We're running 2 workloads on the same core. They're doing a fine-grained mix of CPU-intensive or memory-intensive work, for example, floating point operations of different kinds, integer operations of different kinds. And for each of these, we're plotting the performance of the thread at the top, how much it's slowed down by when it shares its core with the thread on the left-hand side. And you can see that there are some mixes where there's no slowdown at all. So the resources that the 2 threads need are complementary to each other, and the core can run both of them at the same time as if they were in isolation. And then there are other mixes where we get at least a 50% slowdown, sometimes even worse. So particularly if we're running workloads that need some resource that's assumed to be rarely required by the designers, but then workloads come along all needing it at the same time, we get interference in their performance profiles. If we look at the performance of PageRank on this same 2 threads per core, 2-socket system, we can look now at the decisions over where within the system we place the threads, whether they share the same core, whether they're put on different sockets or the same socket. And for a given thread count, we've got a wide range of possibilities. So say with 16 threads, we can spread them evenly across the cores. We can pack them into a single socket and have them share cores. And so we've got this spread where, depending on how well we make those placements, we can get around 30, 40% difference in performance from the best placement down to the worst placement. And the reason for this is that complexity I mentioned earlier in terms of the structure of the machine. We're not just thinking about scheduling the threads onto the individual cores, but the workload demands that those threads are going to bring with them in terms of the memory they're bringing in and out of the caches in the machine, the memory traffic that they're requiring to be brought in and out of the socket, and the communication or synchronization costs as there's communication between the 2 sockets as the job runs. And these are factors that the operating system is not traditionally taking any account of. It's just looking at the CPU demands and not considering the extra resources and how those are going to interfere with each other as the workloads execute. So in each of these issues, I've illustrated how at the algorithm implementation and the runtime system level, we're tackling problems that we traditionally hope would be handled in the operating system on behalf of this software that we're building. So I'm just going to finish by talking about some of the areas in which I think operating systems should evolve in order to better support these kind of workloads, and the ways in which perhaps the hardware at the moment and these example workloads like the graph analytics case have different demands on the hardware and maybe enable different solutions to be employed. So first of all, I think the main functions of the operating system will remain the same. isolating applications from one another so that a fault in one does not cause a fault in the other, so that it doesn't leak data, and that jobs can be terminated if the result is not needed, or the allocation of resources can be tuned between jobs of different importances. Secondly, abstracting the hardware. So mapping the abstractions that the hardware has, which, as I've illustrated, have very low-level engineering concerns, such as how the memory is attached to the sockets, how the sockets are interconnected, and how the relationship between the threads and the cores and caches interacts. And also managing the hardware. As jobs start and finish, deciding how to change these allocations of low-level physical resources to different jobs. But I think the setting increasingly is different now, where instead of having an individual operating system on an individual computer, we should have an operating system that acts at the same granularity as the workloads that are running over the system. So increasingly, that would be a cluster of machines with a distributed workload deployed over it, with Apache Spark and Hadoop being two prominent examples there. And then the operating system acting across the entire cluster rather than running on a single machine basis. And the reason for doing this is that if we look across the entire cluster of machines, or across an entire large complex machine like the multi-socket M7 I've used as another example, then the OS is able to benefit from knowing not just what the CPU demand is on these different systems, but also the more detailed resource demands on the caches, on the memory bandwidth, the interconnect usage, and so on. And so there's the potential for performance improvements by allocating resources more appropriately to an application. And there's also the potential for having more efficient aggregation of workloads if it's possible to pack the workloads together more tightly and still keep good performance while reducing interference between the workloads. And that's a reason at the moment that often machines are dedicated to a single workload, is to avoid that interference by effectively over-provisioning and wasting resources. Secondly, I think the responsibility of the operating system changes. It's increasingly the case that the OS is not responsible for the actual day-to-day bringing in and out of data across disks and across the network. Modern hardware uses techniques like SR-IOV network interfaces that let applications or virtual machines access the hardware directly without intermediating through the operating system on each of those accesses. Technologies like byte-addressable non-volatile memory have the potential for doing that for storage as well. So applications can directly access the data they're using in persistent storage rather than going through a disk-style interface. So the OS then is responsible for the start and end of day operations as jobs start and finish, and for controlling the operations that the applications do, not for the byte-by-byte shuffling of data around. And that's important because with the operating system being responsible just for those longer-term decisions, it's then possible for it to take a view across a larger number of machines, because it's not having to be on the data path for each of the transfers that's made. So I'll just illustrate 3 examples then for how I could see operating systems evolving in this direction, and some of the links with recent work we've been completing. Firstly, just going back to the PageRank example, I would then see, rather than expert programmers being responsible for the kind of decisions that we've taken in the mapping of the algorithm to the hardware, the OS would be responsible for picking between different techniques that the application could be able to employ, and for tuning the use of resources between competing applications of different priorities. So in the case of the PageRank, we might have a description of the access patterns here and the consistency models needed for the different pieces of data. And then system software would be responsible for selecting when to replicate data to use more memory but to make the accesses faster, when to use tiling techniques, when to make mappings of different sizes. If we had multiple copies of this running together, then this could be expressed as an optimization problem based on the importance of the different tasks, the sizes of their data sets. And then perhaps we could take a more principled way of approaching the problem of deciding how to allocate resources to these different workloads rather than on a first-come, first-served style of approach. Secondly, I think the operating system should be responsible for scheduling all of the resources in the machine, not just the hardware threads, as has been traditional. So perhaps in the case of a workload running on the M7 processor, we might do scheduling at the granularity of a complete core cluster rather than a thread-by-thread basis. And we would also consider the interconnect loads and the other resource demands that the workloads have. And this is an area that's attractive because it means that at a small scale, a workload can be tuned to the sizes and features of a part of the machine. And then we're able to gain some sharing by having multiple workloads run together and to compete in cases where the interactions are more straightforward to anticipate than those fine-grained interactions between different kinds of instruction in a core that I was illustrating just now. We've done a little bit of work towards this with students at ETH Zurich, where we're looking at a mix of database parallel join operator algorithms. And we're looking at whether to run them sequentially with full access to a machine, whether to allocate them a core, whether to allocate them a socket, a complete NUMA domain in this graph. And across a mix of data input sizes, we're seeing that allocating a complete socket to one of the operators at a time is more efficient than the very fine-grained or very coarse-grained sharing. And then the final example of services that the operating system could provide in a cluster is having more coordination around the execution of parts of an application. And the example here is going back to PageRank again, but looking at a version built using Apache Spark and running over the Java virtual machine with network communication between different steps of the computation as they need to exchange data. And a problem we've seen in that case is that as the JVM is running, we'll complete some of the iterations of the PageRank algorithm with the JVMs on different machines active throughout, so the blocks here between the red lines. But then occasionally we'll have the garbage collector start on one of the JVMs, and then while that VM is paused completing the garbage collection, then all of the other VMs in the system get stuck behind it, because they're now waiting for responses to come back from the one at the top that's got stuck, and they're not able to make any progress on their own work until those responses are received. So perhaps one future role of the operating system will be to coordinate this kind of activity within a distributed system, rather than making these piecemeal decisions on one VM at a time. And in the case of garbage collection, what we'd like to happen for this workload is to actually synchronize it. So either all of the VMs will be running and doing the PageRank computation, or they'll all stop at the same time, and they'll all do the garbage collection and then continue when they're finished. So similar to ideas of gang scheduling and high-performance computing, we let the threads run together, communicate easily, and then stop them all at once. We've got some initial results here. We're seeing the iterations of PageRank as the different bars, the time they take as the height, and at the top, the current performance where the VMs collect independently, with the shading indicating the number of VMs that had to stop for garbage collection in any step. So what's happening as the computation progresses is that these pauses get spread out across the VMs because of slight differences in the load that they experience. And by the end, we're seeing one VM collecting in most of the iterations. And you can see that even having one VM stop is pushing up the height of the bars above the best case here. And then if we have the extra coordination step and synchronize across the VMs, make them either run all the time or all stop for collection, we have the effect of keeping the same best case performance, achieving the best case performance more regularly during the computation. And the difference between having all of the VMs stop and collect versus having just one of them stop and block the others as they stall up behind it is very low. So we're hiding the GC activity from the threads from the main timed execution part. So these are a few of the areas that we're seeing operating systems evolving and areas that we're working on at the moment with this workload and other examples. We've got some technical details on this material online, either on the Oracle Labs webpage or you're welcome to get in contact on email and I can send more details. We have internship positions and other opportunities in Oracle Labs, so again, very happy to talk with people who would be interested in that, or if you have students or colleagues who might be interested, then also the same address, or happy to talk later today. And I should acknowledge the people I've been working with in this project, colleagues in the broader graph analytics project, and in other parts of the company that have been involved with the performance analysis and evaluation, and also former interns who've contributed greatly to this work, and our university collaborators, UC Berkeley and ETH Zurich. Thank you.
Thank you. Tim, I hope you'll be able to take some questions. There's two housekeeping announcements about this. One is that for questions here, there should be a handheld mic. Okay, you've got that, great. The second thing is that for people who are watching on live stream, you can submit questions. And Jared, where's Jared? You're there and you're monitoring the computer? Or great, okay, thank you. So we'll be able to, you can put up your hand, Jared, if you have a question from the live stream audience. Okay, having said that, there was a question, I think, back there.
Do you recognise the use of GPUs in graph analytics, and would that be an extension of the same idea, or is there kind of bulk copy between different memory architectures a different level of detail than you've considered at the moment?
So we've not worked on GPUs directly in this work at this point. I think I think some of the difficulties would be around the memory access patterns. We'd probably need to restructure the PageRank inner loop to make the accesses maybe done in bulk across a larger block of edges at the same time, so we keep the threads from diverging, and then have some extra work doing the summation and putting the pieces together into the per vertex results. I think probably the important question to look at before doing that will be what the actual peak transfer rates on and off the GPU are. We're benefiting from the fact that these chips can do vast numbers of cache line fetches per second, and we're trying to hit that limit. So if it's possible to have a different processor architectures that can do larger numbers of fetches, then that would help us. So for example, the kinds of machines that Cray and Terra have made in the past with vast numbers of hardware threads and no caches would be a great fit for this. I'm not sure how that relates to current GPU technologies, though.
Thank you. So I can see how this sort of symbiotic relationship between the operating system and the application speeds up an application. But supposing I've got a device that needs to run multiple applications with different characteristics, does that work by sort of hints from the application to the operating system, multiple copies of the operating system? How does that work, please?
So I think exactly how we draw that line between the runtime system and the OS is really the research question that we're trying to address in the next piece of this work. The way I'm picturing it at the moment, the application would expose more information about the ways it's going to use the resources. But one of the challenges is, just think about the PageRank example, exposing almost a menu of different algorithm implementations, where we might want to select between the version that uses cache tiling and the version that does not, based on whether we're running on a large input data set or a small one, or got a large portion of the machine or a small portion. So we're thinking about the problems of multiple workloads, primarily in the sense of different queries to the analytics system at the same time, so maybe different input sets or different graphs. And I agree, it would be interesting to look at mixes between a broader set of workloads as well, maybe the kinds you might have on a mobile device, some doing processing on the device and some doing user interaction would be an example.
I'll cheekily ask another one. I thought you had a really interesting point about the distribution of garbage collection in, for instance, a Spark job. but I wasn't sure why it's an operating system task to schedule this. It seems like it's just about bringing Spark and the JVM closer together so that Spark could organize that synchronicity.
So I think it's something which, it's not traditionally an operating system task, but it's something that maybe could be brought into the domain of responsibility of the OS. So one example is when looking at having multiple JVMs collecting on a single machine, then it can be better to schedule the collections at different times because they have a high impact on the memory traffic that the system sees. And so having that be scheduled with a view of the complete state of the system and whether this set of processes is collecting, so maybe unless it gets super urgent, this other set should hold off for a bit. That benefits from larger scale coordination.
Thank you. Thanks for the talk. Can I ask in what ways you might redesign a core cluster to optimize what you want to do?
So the ability to handle large numbers of random memory accesses would be probably the most significant change the hardware could make. So the hardware I mentioned just now from Cray and Terra was designed so that it would have, I think it was hundreds or thousands of hardware threads, and the hardware would be able to switch between each of them as they're waiting for memory accesses to complete. And so if we were able to have that degree of parallelism, we'd be able to be tolerating the delays bringing data into the chip more effectively. I think another interesting question would be how the complete system could be redesigned. So the relationship between processing and memory. There are several projects working within the broad research community on nearer to memory processing of different kinds. So if we're able to avoid bringing the data all the way into the processor, only to look at one floating point value in it and to discard the rest of the cache line, then that could be an efficiency saving.
Yep, go ahead.
So I could see how synchronizing the garbage collection was a really good idea. I could see that you were sort of telegraphing that earlier on in the talk. But what about external events? There may be sort of cases where the last thing you want is the machine to appear dead because there's a human somewhere going to ask it a question. Or another application.
So there's actually the exact opposite garbage collection policy that we use in settings which are more interactive. So in those ones, we're wanting to spread out all of the collection and so make sure that out of a set of machines, we've got only one, at most one at a time collecting. And one of the reasons for that is that if a response getting back to a user depends on a quorum of 2 out of 3 machines being active, then if we can make sure that at most one is stopped for collection, we can always assemble that quorum and always respond in a timely way. So that was one example of trying to coordinate GC timing to make sure that user-perceptible delay of tens or hundreds of milliseconds is not on the critical path of getting a response back. And I think perhaps some of the other hardware-aware scheduling ideas could contribute there as well. If we're concerned about the skew between the fastest and slowest responses, then being able to keep the parts of the system running user-facing pieces of a workload isolated from the parts that are doing bulk computation, maybe that's going to reduce the likelihood of delays to the user part of the workload. There's been some interesting work recently, I think, from groups at EPFL and from Stanford in these directions.
Okay, are there any further questions? Is there anything from the live stream? Okay. Let me see. I'll have one more here. Everybody gets to ask 2 questions.
Sorry, just ask one quick supplementary question. Are there limits to the degree of fine granularity that you can introduce?
Are you thinking about in terms of the work distribution part? So I need to check the...
Are there limits on granularity?
So it's a fairly smooth trade-off where as we make the granularity smaller, we're adding to the overheads. So I think we tried some experiments distributing individual computations on an individual vertex to threads. I think the difficulty there is that although we can push down the granularity at that level, we're still not subdividing a piece of work. So whichever thread is visiting Barack Obama's followers on Twitter, they've got a big chunk of work that's a single indivisible unit. So for some algorithms, we start adding extra levels of nested parallelism, where we can parallelize within the work on a vertex if there are spare resources and that's a big enough piece of work at the end. But that's getting to the level where we need the C++ program level of abstraction to have different versions of the code that can handle the nested and non-nested cases. So maybe that to someone writing in the domain-specific language, it looks the same, but we're adding alternatives further down and having to select between them dynamically based on the workload.
Any more? Right. One more.
Hi, you showed some interesting plots about how you were getting performance improvements by essentially distributing the problem over multiple cores. It's quite clear and quite easy how you would do that by replicating the data, but then you went on to say how you got improvements from splitting the data. In some ways, maybe I've misunderstood quite what you're doing here, but you end up with a bit of a chicken and egg problem to work out how you distribute, how you split the data, how you partition the data in the first place to get that speed up. Could you explain a little bit more about how you solve that?
So here we're taking a very simplistic approach, and there's been quite a bit of work, as you might have seen, on partitioning graphs and trying to identify portions of a graph with good internal connectivity. What we're actually doing here is just being concerned about the distribution of the parallel work. So looking at the number of edges we'll be visiting in the tile of the graph and looking at the size of that randomly accessed portion of the array. So we're distributing the work efficiently at that level rather than trying to tease apart completely independent parts of the graph, because we're often working on graphs which either don't have structure that's amenable to that, or we're wanting to be robust and not be making assumptions about the graph structure. The other point I should mention there is, of course, another reason for looking at simplistic partitioning algorithms is we don't have to spend a lot of time on the partitioning. We can do that perhaps while loading the graph into memory, rather than needing to have a separate analysis to identify if there is structure present and to exploit it.
So you start with a very coarse algorithm to sort of partition the thing up, split it on that very coarse partitioning, and then run your future algorithms based on that coarse partitioning.
Right.
Okay, thanks.
If there are no more, then I think we can wrap up this session. Thank you again, Tim, for your excellent talk.